September 26, 2022 changed everything we thought we knew about asteroid defense. NASA's DART spacecraft slammed into Dimorphos, a small asteroid moon orbiting the larger Didymos, in humanity's first attempt to deliberately alter a celestial object's path. The mission was supposed to be a simple test: hit the target, measure the orbital change, and prove we could defend Earth from asteroid threats. But what happened next stunned scientists worldwide. The impact didn't just nudge Dimorphos off course, it unleashed something completely unexpected that's still reshaping our understanding of asteroids today. The kamikaze mission DART, Double Asteroid Redirection Test, represented humanity's first planetary defense experiment, designed by NASA's Planetary Defense Coordination Office under the leadership of Lindley Johnson. The $325 million spacecraft launched on November 24, 2021, beginning a 10-month journey to intercept Dimorphos, a 525-foot-wide moonlet orbiting the larger asteroid Didymos. The mission's objective was elegantly simple yet technically challenging: crash into Dimorphos at 14,000 miles per hour, and measure how much the impact changed its orbital period around Didymos. DART carried no scientific instruments for studying the asteroids. It was purely a kinetic impactor, essentially a guided missile designed to test whether humanity could deflect a potentially hazardous asteroid. The spacecraft used ion propulsion and autonomous navigation systems to home in on its target with pinpoint accuracy. Mission controllers at Johns Hopkins Applied Physics Laboratory in Maryland could only watch as DART approached its target, since the 7 million mile distance meant radio signals took several minutes to travel between Earth and the spacecraft. The final approach relied entirely on DART's onboard camera and navigation system to guide it to impact. Perfect impact. At exactly 7:14 p.m. Eastern Daylight Time on September 26, 2022, DART achieved what many considered impossible: a direct hit on a target the size of a football stadium from millions of miles away. The impact occurred with the force of several tons of TNT, creating a spectacular explosion visible to ground-based telescopes worldwide. Andy Rivkin, the mission's investigation team lead at Johns Hopkins Applied Physics Laboratory, confirmed that DART struck within 17 meters of Dimorphos' center, a bullseye by any measure. The impact was captured by DART's own camera in its final moments, showing the rocky, boulder-strewn surface of Dimorphos rushing toward the spacecraft at incredible speed. Simultaneously, LISIACube, a small Italian-built observer spacecraft, photographed the collision from a safe distance, capturing images of the impact plume and debris cloud. Telescopes on Earth, including the Hubble Space Telescope and James Webb Space Telescope, immediately began tracking the aftermath. The impact created a massive debris tail stretching thousands of miles behind Dimorphos, visible as a bright streak against the darkness of space. Initial observations confirmed the mission was an immediate success, but the real surprises were just beginning to unfold. The shocking results. The impact results exceeded all expectations in ways that left scientists scrambling to understand what had happened. Pre-mission calculations predicted DART would shorten Dimorphos' orbital period around Didymos by approximately 10 minutes. Instead, measurements revealed the orbital period had decreased by 32 minutes, more than 3 times the predicted change. Tom Statler, NASA's DART program scientist, called the results remarkable and far beyond their most optimistic projections. The massive orbital shift suggested Dimorphos was much less dense than anticipated, behaving more like a loose pile of rubble than a solid rock. Andy Cheng, the DART investigation team co-lead, explained that the enhanced momentum transfer indicated the asteroid was essentially a rubble pile held together primarily by its own weak gravity. The impact had not only displaced material from the collision point but also triggered a cascade effect where ejected debris contributed additional momentum change. This discovery revolutionized our understanding of small asteroids. Many are apparently fragile, loosely bound collections of rocks and dust rather than solid objects. The finding has profound implications for future asteroid deflection missions, suggesting smaller impactors might be far more effective than previously thought. The debris mystery. Months after impact, Dimorphos continued surprising scientists with its ongoing transformation. Hubble Space Telescope observations revealed that the asteroid was still ejecting material long after the collision, creating multiple debris tails that evolved and changed direction over time. John Yang Lee from the Planetary Science Institute led analysis showing Dimorphos had developed at least 3 distinct debris tails spreading in different directions. The continued material ejection suggested the impact had fundamentally destabilized the asteroid's structure, causing ongoing landslides and surface collapse events. Christina Thomas from Northern Arizona University reported that Dimorphos was losing mass at a rate much higher than expected, with debris continuing to stream away from the impact site months later. Some debris particles were moving fast enough to escape Dimorphos's weak gravitational field permanently, while others were falling back to the surface in slow motion. The European Space Agency's upcoming Hera mission, scheduled to arrive at the Didymos system in 2026, will provide detailed analysis of the impact crater and ongoing surface changes. This extended debris emission was completely unprecedented and suggested asteroid impacts could have much longer-lasting effects than anyone realized. Surface secrets revealed. The impact revealed Dimorphos to be far more complex than a simple space rock. High-resolution images from the final moments before impact showed a surface covered in large boulders, some measuring several meters across, scattered across relatively smooth terrain. Olivier Barnouin from Johns Hopkins Applied Physics Laboratory analyzed the surface features and determined that Dimorphos likely formed from debris shed by the larger Didymos asteroid over thousands of years. The boulder distribution pattern suggested the moonlet surface was actively changing, with rocks gradually migrating toward the equatorial region due to Dimorphos's rotation. Patrick Michel, principal investigator for the upcoming Hera mission, noted that the impact site appeared to be in a region of relatively fine material between larger boulders, which may have contributed to the unexpectedly large momentum transfer. Spectroscopic analysis of the debris cloud revealed that Dimorphos has a composition similar to carbonaceous chondrite meteorites, suggesting it contains primitive materials from the early solar system. The asteroid's low density, approximately 1.17 grams per cubic centimeter, confirmed it was indeed a loose agglomeration of rocks and dust, with significant empty space between particles. This porosity explained why the impact was so much more effective than predicted. Asteroid defense revolution. The DART results revolutionized planetary defense strategies and demonstrated that deflecting potentially hazardous asteroids might be easier than previously thought. Lindley Johnson, NASA's planetary defense officer, announced that the mission's success validated kinetic impact as a viable technique for asteroid deflection. The unexpectedly large momentum change meant smaller, less expensive spacecraft could potentially deflect threatening asteroids with sufficient advance warning. Alan Harris from the Space Science Institute calculated that a DART-sized impactor could deflect most potentially hazardous asteroids if deployed years before predicted impact. However, the mission also revealed critical knowledge gaps about asteroid composition and structure that must be addressed for future defense missions. Amy Mainzer, principal investigator for NASA's Near-Earth Object Surveyor mission, emphasized that better characterization of asteroid properties would be essential for selecting appropriate deflection techniques. The DART success led to accelerated development of the NEO Surveyor Space Telescope, designed to discover and characterize potentially hazardous asteroids before they pose threats to Earth. ESA's Hera mission became even more critical, as it will provide detailed post-impact analysis necessary for planning future deflection missions. The success transformed asteroid defense from theoretical possibility to proven capability. The Hera investigation. ESA's Hera spacecraft, which launched in October 2024, represents the second phase of humanity's very first asteroid deflection experiment. Patrick Michel, the mission's principal investigator from Côte d'Azur Observatory, designed Hera to carry out a detailed forensic analysis of DART's impact effects. The spacecraft is set to arrive at the Didymos system in December 2026, and will spend about 6 months mapping both asteroids with honestly unprecedented precision. Hera is equipped with advanced instruments including a laser altimeter, a thermal infrared spectrometer, and high-resolution cameras that can reveal surface features down to centimeter-scale resolution. The mission will also deploy 2 CubeSats, Juventus and Milani, to study the asteroid's internal structure using low-frequency radar and gravimetric analysis. Ian Carnelli, Hera's project manager, explained that the mission will measure the exact size and shape of DART's impact crater, determine how much mass was ejected, and analyze the ongoing surface changes. Hera will also investigate whether DART created a so-called moonquake that continues to affect Dimorphos' structure. This mission really stands out as an example of unprecedented international cooperation in planetary defense, combining European spacecraft technology with the analysis of an American impact experiment, all to benefit humanity as a whole. Unexpected discoveries. The DART mission, revealed phenomena that scientists never anticipated and are honestly still struggling to explain. Tony Farnham from the University of Maryland discovered that Dimorphos developed multiple debris tails that actually changed direction over time, suggesting there are some pretty complex dynamics happening within the Didymos system. Some of the debris seemed to be following orbital mechanics around Didymos, while other material was just escaping the system entirely. Fernando Moreno from the Institute of Astrophysics of Andalusia used computer modeling to show that solar radiation pressure was sculpting those debris tails into these really intricate patterns that could even be seen from Earth. The impact also appeared to have altered Dimorphos' rotation rate, though of course precise measurements will have to wait until Hera arrives. Masatoshi Hirabayashi from Auburn University proposed that the impact might have triggered landslides and surface restructuring that are still ongoing months after the collision. Spectroscopic analysis of the debris revealed water ice signatures, which was a big surprise given Dimorphos' location in the inner solar system. Simone Marchi from the Southwest Research Institute suggested the impact might have exposed subsurface materials that had been protected from solar heating until now. All these discoveries really showed that even a so-called simple kinetic impact can trigger cascading effects that fundamentally alter an asteroid's properties, behavior, and appearance for quite some time. Global implications. The DART mission's success, honestly, triggered worldwide investment in planetary defense capabilities and led to new international cooperation agreements. NASA announced plans for multiple follow-up missions, including advanced impactor designs and gravity tractor concepts for more precise control over asteroid trajectories. Meanwhile, China's National Space Administration revealed plans for their own asteroid deflection tests, and Japan's JAXA proposed missions that would combine sample return capabilities with deflection experiments. The United Nations Office for Outer Space Affairs began developing international protocols for planetary defense coordination, recognizing that asteroid threats really do affect all nations equally. ESA expanded their Space Situational Awareness program to include enhanced asteroid tracking capabilities. The mission's success also sparked private sector interest with companies like SpaceX and Blue Origin proposing commercial asteroid deflection services. Brent Barbee from NASA. Goddard Space Flight Center is leading efforts to develop standardized mission planning tools that any space agency could use for asteroid deflection. DART's results were incorporated into updated planetary defense protocols which are now shared through the International Asteroid Warning Network. Most significantly, the mission proved that humanity actually possesses the technology to protect Earth from asteroid threats, transforming planetary defense from science fiction into an operational capability that keeps evolving through international scientific collaboration. Future of planetary defense. The DART mission, honestly, marked the beginning of humanity's active role in solar system dynamics, with some pretty far-reaching implications for space exploration and planetary protection. Amy Mainzer's NEO Surveyor mission, launching in 2028, will use lessons from DART to better characterize potentially hazardous asteroids before deciding on deflection strategies. NASA is already developing advanced kinetic impactors with enhanced targeting systems and multiple impact capabilities for dealing with larger asteroids. ESA, on the other hand, plans follow-up missions to test gravity tractor techniques that could offer more precise trajectory control for sensitive deflection scenarios. The success of DART validated kinetic impact as humanity's first line of defense against asteroid threats, but it also made it clear that we need a better understanding of asteroid internal structure and composition. Organizers of the Planetary Defense Conference now use DART results as baseline data for impact deflection scenarios. The mission also established templates for international cooperation in planetary defense that go beyond political boundaries. Johns Hopkins Applied Physics Laboratory continues to analyze DART data to refine impact models and improve future mission designs. Most importantly, DART proved that with enough advance warning and international cooperation, humanity really can actively protect Earth from cosmic threats. The mission transformed us from passive observers of celestial mechanics to active participants capable of altering the trajectories of worlds. NASA hit an asteroid and wow, unleashed discoveries that are still reshaping our understanding of planetary defense. DART's impact on Dimorphos went way beyond expectations, proving that humanity can successfully deflect potentially hazardous asteroids, while revealing just how complex and dynamic these cosmic visitors really are. The mission showed that even small impacts can have massive results, transforming planetary defense from a theoretical possibility to a proven capability. With Hera arriving in 2026 to complete the investigation, we're stepping into a new era where humanity actually protects Earth from space threats. So be sure to subscribe to Stellar Tech for more groundbreaking space discoveries that are defining our cosmic future.